Okay, so we're in the middle of discussing rings and fields. I'll go over the definition briefly. A ring, usually denoted by R, is a set together with two binary operations, addition and multiplication. We actually call them addition and multiplication, defined on R, such that the following axioms are satisfied. First thing is, R has to be an abelian group under addition, and multiplication must be associative, and distributive laws must hold. And we know we went over some examples. Z together with the usual addition and multiplication is a ring. The complex numbers, once again, the usual addition and multiplication is a ring. The set of real numbers, even the set of rational numbers under the usual multiplication and addition, they are both rings. And we went over some examples. Right. And then this theorem, if R is a ring with additive identity 0, then for any AB in R, any two elements that you take from the ring, we must have 0 times A to equal A times 0 to equal simply 0. And these are the two properties. A times negative B is equal to negative A times B, which is equal to negative AB, the product. And then this final law. So we prove this theorem, we have to start from here. We have to continue from here. Okay, so today we will start off by discussing homomorphisms and isomorphisms. So let me write it first of all. Homomorphisms and isomorphisms. So I'll start off with the definition. Okay. Definition. Let's take R and R prime to denote rings. Let R and R prime be rings. Then a map phi from R to the other ring R prime is a homomorphism. This is actually a ring homomorphism. So within brackets, I'll write ring homomorphism. If the following two conditions are satisfied. If the following two conditions are satisfied. So for any AB in R, for any two elements AB that we take from the ring R, first we must have phi of A plus B to equal phi of A plus phi of B. Then the second condition, phi of AB, A times B, must equal phi of A times phi of B. So if you look at the first condition stated over here, phi of A plus B is equal to phi of A plus phi of B. This actually tells you it's a homomorphism between the two abelian groups R and R prime. Now remember, R and R prime are rings. That means they are abelian groups under addition. So this first condition tells you this phi is a group homomorphism between the two abelian groups R and R prime. So this actually tells you it's a homomorphism between the two abelian groups. Between the two abelian groups. Now, the second condition, observe that R and R prime being rings, they have a multiplicative structure. Multiplication is a binary operation defined on both these sets. So, this map phi, it has to relate the multiplicative structures of R and R prime in a similar way as we have with this first condition. First condition that you see, right? So this sort of gives you that relationship between the two multiplicative structures in R and R prime. Let's go over some examples. Okay. Let's take capital F to denote the set containing all functions f from R to R, the set of real numbers. Where f is from R to R. So this capital F is containing all real valued functions f from R to R. And this example we have done before when we were actually going over the group theory stuff. So we know that f together with addition is an abelian group under the usual function addition. And we have not defined the multiplication or the multiplicative structure. We have not seen that for f. So let's define it right over here. So let me write, we know that f together with addition is an abelian group under the usual function addition. Right? What do we mean by that? If you take two functions f and g, both of which are from R to R, then f plus g of x for any real number x is given by f of x plus g of x. Now we define multiplication on f also in a similar way. So we define multiplication on f by f times g of x, where x is any real number, to be f of x times g of x. So the product that you see over here is the usual product between two real numbers, right? Okay. Now, before we define or we look at a ring homomorphism, we get onto that example. Let's see that this is indeed a ring under the addition that we already know, and this multiplication we just defined. Multiplication is associative, first of all. Multiplication denoted by this cross is associative. Right? Let's take, how do we see this? Let's take F, G, H to be elements in the set F. So F, G, and H are functions from R to R. And so for any real number x. Any x in R. We have f times g times h, right, of x is equal to, by this definition of multiplication on f, we have f times g of x times h of x. Once again, applying the same definition for this function over here, we have this to be f of x times g of x h times h of x. Now remember, for all these functions, f, g, h, they are real valued functions. So f of x, g of x, and h of x, for every real number x, gives you another real number. All these are real numbers, and we know the set of real numbers is actually a ring. So the multiplication that you see over here is the multiplication that's defined over R. And because it's a ring, it's associative. So we use the property that multiplication defined on R is associative, and we write f of x times g of x h of x. This is because all these numbers that you see are real numbers. R is a ring. Multiplication is associative, therefore, we write it this way. Now, once again, putting all this back together, going back to this definition, g of x times h of x, with this definition we see is g times h of x. Once again, going back to the definition of multiplication over f, we see that this is f times gh of x. So associative property holds. And the distributive laws also hold. I'll show you one distributive law. The other one follows a similar way, which you can do on your own. So f times h plus g of x, right? Now, h plus g, for h and g elements in f, is also an element in this set. So we have two elements in the set. Going back to this definition of multiplication on f, we write it as f of x times, h plus g, or you can even write g plus h, doesn't matter because it's an abelian group and addition of x, right? Now, f of x times, we have h plus g of x to be h of x plus g of x. What do we have now? F of x, h of x, and g of x, all of which are real numbers. The set of real numbers is a ring. So the distributive laws hold over there. Using that property, we can write it as f of x times h of x plus f of x times g of x. Now, this, once again, going back to the definition of multiplication over f, is given by f times h of x plus f times g of x. Exactly what we wanted to prove. And the other multiplicative law, the other distributive law also holds, and you can do this on your own, following a similar method. So all conditions are satisfied for this particular addition and multiplication defined over f, the set which is containing all functions f from R to R is a ring. So this is a ring. So we write F is a ring under the addition and multiplication we just defined. Right. Now, let's consider F and the ring of real numbers. This F, which is also a ring as we just now proved it, and the ring of real numbers, right? And let's take an element A in R. Consider the rings F and R, and let's take A from R. Let's take A, any real number. And we define the evaluation homomorphism, which we have to actually prove that this is indeed a homomorphism. The evaluation homomorphism. P of A from F to R is defined by P sub A of F equals F of A. For each function or element F, we take from the ring capital F. Okay. Now, we actually have seen that this evaluation homomorphism is a group homomorphism for F and R, right? So all we've got to do is show that the second condition, this multiplicative condition holds in order to show that this phi sub A is a ring homomorphism. We have done this example when we were discussing homomorphisms in group theory. So let me write it out. All right, we've already showed that. This is a group homomorphism. So F under addition, or group homomorphism between F and R. Let's put it that way. Now, to prove that the second condition holds in order to show that it's a ring homomorphism, now phi of A of Fg. Let's take F and G, any two elements from this ring capital F. So phi sub A of F times G, by definition of this mapping, is given by Fg of A. And the way we defined multiplication over F allows us to write this next one, F of A times G of A, right? And F of A, once again, going back to the definition of this mapping, we see is simply phi sub A of F times, phi sub A of G, exactly what we wanted to show. And this is true for any Fg that we take from the ring F. Therefore, the second condition, the two conditions for this mapping to be a ring homomorphism are satisfied. So we conclude that this is a ring homomorphism. I will simply write a homomorphism. For now, I'll put within brackets ring is a ring homomorphism. Is a ring homomorphism. Okay. Okay, let's take a look at another example. Okay, let's define a mapping phi from Z, which is a ring, to the ring Zn. This also we saw last time is a ring under addition modulo n and multiplication modulo n, and Z under usual addition and multiplication. Defined by phi of A, the remain. Let's define phi of A to be the remainder of A modulo n. So we take an integer A through this mapping, we take its remainder when divided by n, which is an element in Zn. Now, this mapping is a ring homomorphism for each positive well. It's a ring homomorphism for each positive when. We have already shown this when we were once again discussing homomorphisms in group theory, that the first condition for the ring homomorphism, where it's a group homomorphism when considering these two groups under their usual addition, is a group homomorphism. Right? So we only have to consider, or we only have to show the multiplicative property. So I'll write, we have already shown that for A, B in Z, we have that phi of A plus B is simply phi of A plus phi of B. See, so we only have to prove the multiplicative property. Right. So to show the multiplicative property, we take to show the multiplicative property. What is the multiplicative property? We have to show that phi of A times B, where A and B are two integers, is equal to phi of A times phi of B. When I say times over here, this product that you see, this multiplication over here is multiplication modulo n, right? Okay. To show that the multiplicative property holds, we take A, any integer, to be of the form Q1 times n plus R1 using the division algorithm. So what are we doing in this instance? We are taking A divided by n, and using the division algorithm, we find this quotient Q1 and the remainder R1, which is from 0, which is a number between 0 and n. And take B, we do the same thing with B. Divide by n, find the proper quotient and the corresponding remainder. This is by division algorithm. Where this R1, R2 is, they lie in this range. Right? Now let's find, so what is the value that you get for, we know that phi of A is then given by R1, phi of B produces R2. Why is that? If you go back to this, this is defined. We define phi so that phi of A generates the remainder of A modulo n, the remainder of A when divided by n. Using division algorithm, we can write A and B in this form to find the corresponding or the respective remainders. Therefore, we know that by definition of phi of A is the remainder, the number that you get over here as the remainder of A when divided by n. Phi of B are 2. Okay, so we know that phi of A, phi of B, they are R1 and R2. Then what should we have as phi of A? Let me write. Now, phi of A is an element in Zn. Phi of B is an element in Zn. Therefore, when you multiply elements in Zn, you have to do multiplication modulo n. So I will put it as this, right? So you have R1 multiplication modulo n, R2. So as the answer of the product, what we get is the remainder of R1 times R2 when divided by n. So this product actually gives you the remainder of R1, R2 when that number or when that product is divided by n. Now let's go back to the integers a and b. So we have a, b over here. Let's consider its product in z, a times b, because that is what we have to consider over here. A and b, you can write it as, let me put it over here, q1n plus r1 times q2n plus r2. When you take the product from this first term, we've got q1, q2, n squared, so I'll retain 1n, r1, q2 plus r2q1 times n, and this last number r1, r2. So when you now observe A and B, the product gives you a multiple of n plus a number r1, r2. So when you take this number and apply this function that you see over here, this mapping, phi of AB, then should give you the remainder when you divide this whole number by n. So in this summation, the first term is already divisible by n. So the remainder that you get from by dividing the first term in the summation is 0, right? So we have 0 plus the remainder of R1 plus R2 when divided by n. When you add 0 to any number, right? In Zn or even in any additive group with their corresponding zeros, what you get is whatever the non-zero number, whatever the other number that you're adding to 0, right? So what do we get as phi of AB in this case? That is simply the remainder of R1, R2 when divided by n. Exactly what you get over here. So let me write it. Therefore, phi of AB is simply the remainder of R1, R2 when divided by n, when you divide it by n. Therefore, by definition, we have phi of AB to equal phi of A times phi of B. We don't have to put multiplication modulo n because we understand when you write this product, we are referring to the multiplication that's defined on Zn. Both conditions are satisfied. Therefore, we know that phi is a ring homomorphism. I will put simply homomorphism. Okay. Now let's get to the other definition. definition. An isomorphism is what we call a bijective ring homomorphism. So if you take two rings R prime, if you have a homomorphism between these two rings, and if the mapping is 1-to-1 and onto, we say that the given mapping is an isomorphism, and the two rings are isomorphic. They retain the same structure. An isomorphism P from R to R prime, where R and R prime are two rings. From a ring R to R prime is a homomorphism. So we actually mean a ring homomorphism. Is a homomorphism that is 1-to-1 and onto R prime. If such an isomorphism exists, if such a homomorphism, a bijective homomorphism between R and R prime exists, we say that R and R prime are isomorphic. The rings R and R prime are then isomorphic. We say that these two are isomorphic. Right. Now, before we get to more examples, let me give you this definition as well. So this first definition essentially talks about a bijective ring homomorphism. It's a bijective ring homomorphism. Okay, now the next definition, a ring in which the multiplication is commutative is what we call a commutative ring, right? When you say a ring is commutative, we are referring to specifically the binary operation multiplication that is defined over that, because R is commutative under addition anyway. R together with addition is an abelian. So addition is commutative, right? So when you say a ring is commutative, we are saying we are actually talking about commutativity of multiplication. A ring in which the multiplication is commutative is a commutative ring. And a ring with a multiplicative identity element is a ring with unity, and it's usually denoted by 1. Right? So let me write a ring with multiplicative identity element is a ring with unity, and this is what we call the multiplicative identity. And is denoted by 1, the multiplicative identity. 1 is called unity. This is what we call unity, right? Okay. Now, one important remark I'll put over here before we get to the next example, right? So 1 is a multiplicative identity, right? This is what we call the unity. A ring may have the unity 1. We will go over some examples. Now, if we have 1 plus 1 and n terms in this addition, so we say n summons, times 1 when you add it, m times over here, so we have m summons, is actually equal to n times m summons, right? N summons. So once you consider this product, in the product you have in a summation of this unity, the unity will appear nm times in the summation. Summons. In other words, if we take n times 1, right? That is exactly what we see in this first term in the product. You add 1 n times. So n times 1. This is the multiplication that is defined over some group, right? So when I say n times 1, I'm referring to that multiplication. Times m times 1 is equal to nm times 1. Okay, with this remark, we move to the next example. Let R and S be integers that are relatively prime. In other words, their greatest common divisor is simply 1. They have no greater common divisor other than 1. Then we know that Z sub RS, which contains RS elements from 0, 1, 2 up to RS minus 1, right? So this contains elements 0, 1 up to RS minus 1. For example, Z5 would contain elements 0, 1, 2, 3, 4, right? So Z of RS contains these elements. And then we have ZR cross Z5. So this is a direct product of two groups, ZR and Z5. It has elements given in ordered pairs. How many elements? Once again, RS number of elements. Both these groups are cyclic abelian groups of order RS. They both have the same number of elements RS, R times S. They are both abelian groups and they are cyclic, right? So these two are cyclic abelian groups of order Rs. We already know this group ZRS is generated by the element 1, right? And this direct product is also generated by this ordered pair 1, 1. This is a generator for this group. Now, because we have not done examples of groups of this form, let's go over this example a little bit to understand the type of elements and how the binary operation is defined on this group. Let's take a specific example. Let's take Z2 cross Z3. Now we know Z2 contains elements 0, 1, Z3 contains elements 0, 1, 2. And we are building ordered pairs out of these elements. We have the first element 0, 0, then 0, 1, then 0, 2, then we have 1, 0, 1, 1, and 1, 2. So we have 1, 2, 3, 4, 5, 6 elements. Here the order of this is 2, order of this group is 3. So in this group we have 2 times 3 elements, which is 6, right? Now, like I told you earlier, this is generated by 1, 1, which you will see is the unity of this ring as well. It's a ring. It's a ring as well. Okay. Now, how do we define addition over this group? What we do is we add component wise, and the addition would be addition modulo. For the first component, it will be addition modulo 2. Second component, it will be addition modulo 3. For example, if we take 0, 1 plus 0, 2, so we add component wise. First components always come from Z2. So when you add elements that are in the first component, we pick the addition defined on this group, which is addition modulo 2. When it comes to the second component, all elements come from the group Z3. So when you add those, we actually pick addition, which is defined over Z3, which is addition modulo 3, right? So we have 0 addition modulo 2, 0, which simply ends up being 0. 1 addition modulo 3, 2. So we have 0. 1 plus 2 is 3. Divide by 3, you take the remainder. You have 0, right? So first component, I will simply put addition, the usual addition, because it's done component wise, and for each component we have to refer to uh, addition modulo, whatever the number that appears over here, right? First component in here, we have addition modulo 2. Second component, addition modulo 3. Now, this group is generated by this element 1, 1. Let's see, 1, 1 raised to the power of 1 is simply 1, 1 generates this element, right? Then we have 1, 1 raised to the power of 2 is simply 1, 1. The element added to it again. In other words, we can write this as 2 times 1, 1. I will actually, I will stick to this notation instead of taking this power notation, instead of writing the power of 1, 1. Or no, I should put it this way. 1, 1 to the power of 2. Instead of considering this notation, I'll go with 2 times 1 plus 1, right? This equals 1 plus 1 modulo 2, which gives you a 0. 1 plus 1 modulo 3, 1 plus 1 is 2. Divide by 3, take the remainder, you have a 2. Then we go with 1, 1 to the power of 3. In other words, 3 times the element. You have 1, 1, 1, 1. You add the same element 3 times. So 1 plus 1 plus 1 modulo 2. You have a 1. Then the last element, 1 plus 1 plus 1 is 3. Divide by 3, you take the remainder, which is 0. Then we have 4 times 1, 1 gives you addition of the same element 4 times. So the first element, the first component 1, you add 4 times modulo 2. When you add it 4 times, you get a 0. 0 modulo 2 is simply 0 because 4 is divisible by 2. You add 1 4 times, you get a 4. Divide by 3, take the remainder. You have 1. You have 0, 1. 5, 1, 1 would simply be 5. The first component will be 5 divided by 2, take the remainder, which is 1. 5 divided by 3, take the remainder, which is 2. Now we have 6, 1, 1. 6 divide first component, you add 1 6 times. So you have 6 divided by 2, or simply referring to this remark over here, right? 6 divided by 2, take the remainder, you have 0. Second one also 0 because 6 is divisible by 3 as well. All elements are generated, right? All elements are generated simply by 1, the element 1, 1. So we see that this is actually generated by this 1, 1. How do we define now? This is how addition is defined. Multiplication is also defined a similar way. We multiply component wise, but when you compute the value of the first component, that would be multiplication modulo 2. Second component will give you to compute the second component, you have to take the product or multiplication modulo 3. Right? So that is how we are going to define multiplication for this structure as well. So now you have multiplication and addition defined. Multiplication is commutative. All these you can do on your own and see that this is truly a ring. Right? So we are moving back to the examples. We understand how the additive structure, multiplicative structure works for this group. Right? Now what we are going to do is we are going to define we are going to see that, where is it? ZRS and ZR cross ZS, where R and S are relatively prime, they are isomorphic rings. Those two are rings on their own, and we are going to see that those two are isomorphic rings. Back to our example. Okay, let's define P, a mapping from ZRS to the direct product of ZR, ZS by P of n. You take any n over here. Now n will be a number from 0, any integer from 0 to rs minus 1, right? And this we can write as any integer that you take from this, we can write it as n times 1, right? Because remember, 1 generates all of ZRS, right? 1 generates all of ZRS. So you can take any element from here and write it as n times 1, where 1 is that unity in this ring. And map it to n times the unity that's in this ring, right? Now remember, if you compare the computations done over here with this number, here you have 2 times 1, 1, 3 times 1, 1, 4 times 1, 1, 5 times 1, 1. These are all elements that are in this group, right? That are in this group. So with this n, and once you take the product by 1, 1, you generate an element in this group, right? For any n that you take, sorry, for any n that you take from here in this group. Right. So now this is, first of all, now we are going to show that this is an isomorphism. How do we prove that it's an isomorphism? We simply refer to the definition and show that it's a bijective ring homomorphism. So we had to show that it's a bijection plus a ring homomorphism. So what we are going to do is we will first of all show that phi is an additive group isomorphism. What information do we get from that? We prove that it's a group homomorphism plus it's a bijection. And then separately, we will show that the multiplicative condition also holds, right? We will show that an isomorphism First note that P is an additive isomorphism. Additive isomorphism. What does this mean? It's a bijective group homomorphism. That is, P is a bijective homomorphism, right? So first we will show that it's a bijection, then we will show that it's a group homomorphism, right? The one-to-one condition holds if we have phi is, no, let me write phi is 1-to-1. This is because if we have phi of n to equal phi of m, this implies by definition of this mapping, phi of n times 1 is equal to phi of m times 1. This implies, once again referring to the definition, we have n times 1, 1 equal m times 1, 1. Now observe, what does this give you? If you once again go back to this example as a referral, n times 1, 1 means you are adding the element 1, 1 n times. And on the other hand, we say that it's equal to, or we get the same thing when you add 1, 1 m times. So now addition is done component wise. You add the first component n times uh, modulo R. You add the second component n times modulo S. And when you go to this other side, this tells you once you do that, you should get the same answer if for the first component you add it m times modulo R, and for the second component when you add it m times modulo S. All in all, we can conclude that the only possibility of that even happening would be to have n equals m. So this simplifies to this. N should equal m, otherwise we can't have this one. Right? So phi is 1-to-1. Now, in order to show that it's onto, let's take any value from ZR cross ZS. Let's take PQ, this ordered pair from this direct product. Right? Now, we know that this product, this direct product of the two groups, is actually generated by the element 1, 1, this ordered pair. It's generated by this ordered pair. And so any element that you take from this set must be generated or a power of this element. That means we must have for some n, we have for some n, in 0, 1 up to Rs minus 1, right? N times 1, 1 to equal PQ, right? So when you go to the definition of this function, we have n times 1, 1 to equal phi of n times 1, right? This is simply equal to P of n. So this ordered pair has the pre-image n through this mapping. Now observe, um, we have proved that phi is a bijection, right? We have shown that it's 1 to 1 and it's on to. So phi is a bijection. Now we have to show that it's a, now observe that this n is actually taken from ZRS because these are exactly the elements that it contains. Okay. Now we prove that it's a group homomorphism. So let me write to see that it is a group homomorphism. Right? Group homomorphism under addition. Phi, now you're taking n and m from the set of integers. So n plus m, the usual addition we know, is equal to, by definition of this function phi over here, we can write this as n plus m times 1, right? Times 1, which is equal to n plus m times 1 comma 1. Now, this means this is equal to, we are adding this element n plus m times. We are adding this element n plus m times. In other words, we have n plus m summons. So what do? We sort of group all these components because we are adding the same element. We are taking the first n summons and group it together. Then we take the next m summons because altogether we have n plus m summons, group it together so that we have uh, let's group n summons over here, m summons. From here, we see that this is equal to n times 1, 1, right? If we refer to this remark, it's actually stemming from the remark itself. No, we will use the, sorry, we will use the remark when we are proving the multiplicative part, right? This is m times 1, 1. What I wanted to really say was if we refer to this computation over here, right? Okay. Now, going back to the definition of phi, we see that this is simply phi of n plus this is simply phi of m. So we see that phi is a group homomorphism. If we consider Z, sorry, we are going, P is actually from ZRS to this direct product. So addition over here refers to addition modulo RS. So we have to keep that in mind, okay? Early on I said addition under integers, but no, we are actually looking at the group ZRS, so it's addition modulo RS. So we see that it's a group homomorphism. Now we only need to check the multiplicative condition. To check the multiplicative condition, let's take phi nm. This by definition of phi is nm times 1. This is simply equal to nm times 1 comma 1, the component, the element that you take from the direct product. Now this, in order to solve this, we refer to this remark which we stated earlier. Nm times 1 we can write as n times 1 plus, times m times 1. So n times 1 comma 1, which is the unity in this group, times m times 1 comma 1. Exactly what we wanted. This by definition of phi is phi n, phi m. Therefore, phi is an isomorphism of the rings. So these two rings are isomorphic. I want to come back to this example and correct something. Early on, like I told you, I said n plus m taking two integers under usual addition. No. And I said that it's actually because we have defined it on ZRS. So one thing that we have to make sure there is slight mistake over here the way it's written. Phi of n plus m. N and m are taken from ZRS. So when you say n plus m, what we mean over here is addition modulo RS. So you have n plus m. Add those two numbers, divide by RS, you take the remainder. The remainder must appear over here times 1, right? And then you have that remainder times this element that's taken from the direct product, right? So we leave it at that. We go on to look phi of n and phi of m, right? So I'll just scratch this part out, and this has to be addition modulo RS. I'll put it this way, okay? So phi of n by definition is n times 1, 1. What do we do in this case? We take the first component, you add it n times, divide by R, because it's a direct product ZR cross Z5, divide by R, you take the remainder. Second component, you add one n times, right? So you have n divided by R, divided by S, you take the remainder. When it comes to this value over here also, you get an element, first component, you add 1 m times, divide by R, take the remainder. Second component, also same, take m, divide by S, take the remainder. Once again, you have two ordered pairs. What do we do? The usual addition defined on this direct product. Take the first component that comes from this summation, take the first component that comes from here, add those two, divide by R, take the remainder. What do we get? The same number that you get over here when you compute this, right? When you compute this. So the way I wrote it down is incorrect because I suddenly moved back to the set of integers, but no, phi we defined on from ZRS to the direct product ZR, Z5. So I wanted to correct that one. The rest is okay. Moving on from here, from this example, Right. Before we get to the next definition, let me go over something. Let's take R, the set, only to contain 0, right? Only to contain 0. So addition, we only have one element. Addition, we define 0 plus 0 to simply contain 0. And 0 times 0, the multiplication will also simply give you 0. This R is a ring under this addition and multiplication we just defined. And we call this the 0 ring. It doesn't really add anything to structure. It only has this one element. So R is a ring called the 0 ring. R is a ring which we call the 0 ring. Right? 0 in this case is the additive identity as well as the multiplicative identity. Because you take 0, multiply it by 0, you get 0. So it's a multiplicative identity and it's also the additive identity. This is the only case where 0 can be both the multiplicative identity and the additive identity, right? So 0 is the additive identity as well as the multiplicative identity. Right. Now let's move to our next definition. The next definition. Let's take R to be a ring with unity denoted by 1, which is different from 0. So we are excluding the case where we would encounter the 0 ring, right? Definition, let R be a ring with unity 1, which is different from 0. So this R can never be the 0 ring because only in the 0 ring we can have the unity to be 0. And let's take any element A in this ring. A multiplicative inverse of A is an element usually denoted by A inverse, which also is in R, such that A times A inverse equals A inverse times A is equal to the unity, right? A multiplicative inverse may exist or may not exist, depends on the ring. If such a multiplicative inverse exists, it must be unique, right? So this is unique if it exists, right? Okay, so this is what we call the multiplicative inverse. Obviously, when you take a ring R, it's an abelian group under addition. So the additive inverse will always exist for every element. The multiplicative inverse, not always. In certain cases, yes. Okay, so if we have R star to denote all the non-zero elements, right? And if it is closed under ring multiplication, multiplication that's defined on the ring. It will only be a multiplicative group if multiplicative inverses exist for each and every element, right? If R denotes the non-zero elements of R and is closed under ring multiplication. It's closed under ring multiplication. Then R star will be a multiplicative group if multiplicative inverses exist. If multiplicative inverses exist. Now we encounter something very interesting. R star, now first we start off with the ring R, right? From this we choose all the non-zero elements. So what we are actually doing here is take R, simply exclude 0, take the rest. And in this next statement it says, once you have this R star, if it is closed under ring multiplication, multiplication is a binary operation defined on R. But it doesn't have to be closed under multiplication when we simply take the non-zero elements. Not always. It's not always the case because there could be non-zero elements where in the product produces a 0, that is, which is not in R star. So R star, all the non-zero elements under that usual multiplication that is defined over R must be closed under multiplication. And if for every element the multiplicative inverses exist in R star, I mean, then R star is a multiplicative group. R star, right? If you look at one example, what I mean by this. We know that, let's go with Z4 is a group, 1, 2, 3, right? Now let's simply take all the non-zero elements. What do we have over here? When we say non-zero, we are simply disregarding 0, take the rest. 1, 2, 3. So Z star 4 will contain 1, 2, 3. Is this closed under multiplication? No. Observe that 2 is an element in Z star 4, and when you take 2 times, now how do we define multiplication over the ring Z4? We define multiplication modulo 4. Define multiplication modulo 4, so I'll write it over here. 2 times 2 is 4, divide by 4, take the remainder, you get a 0. 0 is not an element in Z4 star. It is an element in this ring, but not in the not an element over here. Therefore, Z4 star now is not closed under multiplication. This is what we meant earlier. It's not closed under multiplication. Therefore, this will not be a multiplicative group anyway. Right? Okay. Right. Now, if we consider another example, let's say Z, the ring containing integers under usual addition and multiplication, right? Now, this is a ring with unity. It has 1. 1 is different from 0. So let me write Z is a ring with unity 1, which is different from 0, right? If you consider Z star, that means it contains all the non-zero integers. Now this is closed under multiplication. Now this simply means Z take out 0, right? All the non-zero elements. This is closed under multiplication. Why? You take any non-zero, any two non-zero integers, multiply those two, you get a non-zero integer. You get a non-zero integer. Therefore, we know that this is closed under multiplication. It's closed under multiplication. But do we have, for it to be a group under multiplication, every element in the set must contain a multiplicative inverse. But we know multiplicative inverses exist for 1 and negative 1. Note that 1 times 1 is equal to 1. Negative 1 times negative 1 is equal to 1. So 1 has the multiplicative inverse, which is 1. Negative 1 has the multiplicative inverse, which is itself, that is negative 1. But do we have a multiplicative inverse for 2? No, we do not. 2 multiplied by some integer, can we get 1? No, the only option would be to multiply it by 1 over 2, which is a rational number. Right? We do not have inverse for 2. Therefore, Z star under multiplication is not a group. Is not a group. Right. Let's move to the next definition. Definition. Let R be a ring with unity, which is different from 0. An element U in R is a unit of R if it has a multiplicative inverse in R. If it has a multiplicative inverse in R, right? And if every element, every non-zero element of R is a unit, then we say that R is a division ring or skew field. If every non-zero element of R is a unit, then R is a division ring. Then we say that R is a division ring. Or I'll just write or skew field. Right? So field, with this, we go to the definition of a field. A field is what we call a commutative division ring. So a field is a commutative division ring. What do we mean by that? We start off with a ring. It's a ring which is commutative. In other words, multiplication is commutative. Not only that, every non-zero element of R is a unit. In other words, what does it mean? Every non-zero element has a multiplicative inverse. Every non-zero element has a multiplicative inverse, right? So a field is a commutative division ring. Now, if you go back to this example once again with Z, we see that the only units in Z are 1 and negative 1 because no other non-zero element will have an inverse in the ring Z, the ring of integers. So the only units would be 1 and -1. Therefore, Z is not a field, right? If you go back to the previous example, the only units in Z are 1, -1. Therefore, because not every other non-zero element is a unit. Therefore, it's not a field. Therefore, Z is not a field. Right. Let's find units of this ring. Another example. Let's go with Z6. So this has elements 0, 1, 2, 3, 4, and 5. Right. Now observe. The only units for this ring would be 1 and 5. Right? Would be 1 and 5. Multiplicative inverses. Multiplicative inverse of 1 is 1. This is easy to see why. 1 multiplication modulo 6, 1 would simply be 1. And the multiplicative inverse of 5 is once again 5. Why do we have this? 5 times modulo 6, 5. You have 25 divided by 6. Take the remainder. You get 1. So 1 has itself to be its multiplicative inverse. 5 as the multiplicative inverse has the multiplicative inverse 5. So 1 and 5 are the only units. The other elements you can check and see, but none of those will be units. Now observe, if you look at all these elements and compare it to 6, right? The only units that we have are 1 and 5, which are both relatively prime to 6. So that is one important observation here. Let me write the only units are 1 and 5, both of which are relatively prime to 6, both of which are relatively prime to 6. And we know that units in Zn are precisely those elements that are in Zn, which are relatively prime to n. So as a remark, I will write units in Zn So we know that Z6 is also not a field because two um, 2, 4, 3, all these elements, they don't have multiplicative inverses. Therefore, it's not a field. Units in Zn are precisely those elements M that you take from here, which are relatively prime to n, such that the greatest common divisor of M and N is equal to 1. They are relatively prime to each other. Right? Now, if you look at the group, the ring Z5, which contains elements 0, 1, 2, 3, 4. Now, every non-zero element, 1, 2, 3, 4, is relatively prime to 5 because 5 is a prime number. It's only divisible by 1 at 5. All these non-zero numbers are relatively prime to 5, right? Therefore, we must have all of these non-zero elements in this ring to be units. And they are units. It's easy to see. They all have multiplicative inverses. If you look at it, when you multiply modulo 5, 1, you get 1. Then you have 4 times 4, which is 16. Divide by 5, take the remainder, you have 1. Then we have 2 times 3, which is 6. Divided by 5, take the remainder, once again 1. So the multiplicative inverse of 1 is 1. Multiplicative inverse of 4 is 1. Multiplicative inverse of 2 is 3. Multiplicative inverse of 3 is 2. All of the non-zero elements in Z5 are units by definition because they all possess multiplicative inverses. Therefore, and we know that multiplication is commutative, right? Multiplication is commutative, and every non-zero element in Z5 is a unit. Therefore, it's a division ring. By definition, Z5 is a field, right? So let me write all those information. All non-zero elements are units. Therefore, Z5 by definition is a division ring. Since multiplication modulo 5 is commutative, Z5 is a commutative ring. So by definition, it's a field because it's a commutative division ring. We know that this is a field. Now observe 5 is a prime number and you will see that Zn is only a field when n is a prime number, right? So I'll write it as a small remark next. Zp, why do we have this? It's easy to see, is a field for every p prime. Why do we have this? If we look at this, the addition, multiplication, they're all well defined. We know that this is a ring and multiplication is commutative. Now we only have to look at all the non-zero elements and see whether they end up being units. If you go back to this remark over here, right? Units in Zn are precisely those elements that you take from Zn that are relatively prime to n. So when it comes to Zp, and p is a prime number, what sort of elements do we have in Zp? We have all the elements starting from 0, 0, 1, 2, up to p minus 1. All the non-zero elements are relatively prime to p. All the non-zero elements are relatively prime to p. So all the non-zero elements must be must be units. So by definition, that's a division ring which is commutative, therefore is a field. Therefore is a field. Okay, let's move on to the next definition. And we'll come back to this discussion once again. Definition of a subring. A subring of a ring of a given ring R is a subset of that ring, which is also a ring under the induced operations. For example, you have the ring of real numbers. Then we know the ring of integers. They have the same addition and multiplication that we know of. And Z is a subset of the set of real numbers. Therefore, Z is actually a subring of the ring of real numbers. Okay, so let me put down the definition. Subring of a ring is a subset of the ring that is, let me, subring of a ring R is a subset of the ring R that is a ring on its own under the induced operation from R. But what we mean over here is the addition and multiplication defined on R. If this subring, this subset that you take from R under these two binary operation becomes a ring on its own, we say that it's a subring of R. Induced operations from R. Right? Okay, let's go over one problem. Show that this set, usually denoted by, this is actually a ring, it's actually a field, Q of root 2, field generated by the square root of 2, containing elements of the form A plus B times square root of 2, where A and B are rational numbers, with the usual addition and multiplication. Is a ring. Is a ring and is a subring of R. So we are actually showing it's a subring of R. I'll put it within brackets because if it is a ring under usual addition and multiplication, which is defined on R, by definition, it's a subring. By definition, it becomes a subring. Right. First, we actually have to show that this is an abelian group under addition, right? We know that we can see that it's closed under addition. First, let me write the set over here. Q of root 2 contains elements of the form A plus B times root 2, where A and B are rational numbers. They come from the set of rationals, right? First, we know that Q of root 2 together with addition is an abelian group. To see this, we want to show that it's closed under addition, right? And then commutativity holds because these numbers are real numbers. Addition is commutative in the group R. Therefore, addition over here also is commutative. It's an inherent property. No. First observe that is commutative inherent property. So it's an abelian group, right? It's an abelian group. Okay. First, we show that this set is closed under addition. Take any two elements. Let's go with A1 plus B1 root 2 and A2 plus B2 root 2 from this set, right? It's easy to see when you add these two elements, you get an element of the same form, an element in this set. So you have A1 plus B1 root 2 plus A2, the second element, and the addition will yield. You can add A1 plus A2, and factoring out a root 2, we see that this is B1 plus B2 times root 2. Now A1, A2, B1, B2, they all come from the set of rationals, which is a group under addition. So it's closed under addition. That means A1 plus A2 is a rational number, B1 plus B2 is a rational number. You have a rational number plus rational number times root 2. This is an element in this given set. Therefore, it's easy to see it's closed under addition. And this has the identity of this group is actually 0. It also takes this form. How can we write it? We can write 0 as 0 plus 0 times root 2. Why is that? 0 is a rational number. So we simply replace A and B by 0. Not only that, you take any number in this set and add a 0 to it, you end up with that number. So we understand this is the identity. Now these things you can work them out with more details. I'll just simply state all this. Now to find an inverse of an element, let's take inverse of A plus B times root 2. And this is given by negative A, negative B times root 2. Why is that? When A and B are rational numbers, negative A, negative B are also rational numbers. Once again, it's a ring. And these are the additive inverses. Not only that, when you add these two numbers together, A plus B times root 2 plus negative A, negative B times root 2, what you get is 0, the identity of this group. So the inverse for any element that you take from the group exists. Therefore, it satisfies all the associative property is also inherent. I'll write it associativity, because addition, the associativity property holds for any in the additive group of reals. Therefore, it's also an inherent property. There's nothing to really show in that case, right? All conditions are satisfied so that we understand this given set over here is actually an abelian group because addition is commutative. Once again, an inherent property. It's an abelian group under addition. So one is out of the way. We have shown that this set is an abelian group under addition. Now we know that multiplication is multiplication is also associative. Why? It's also an inherent property from R, right? It is also an inherent property that you get from R. Not only that, the set itself is closed under multiplication. Multiplication is a well-defined binary operation over Q of root 2 as well. So let me write. Under the usual multiplication, why do we have that? If we take A1, B1 root 2 and A2 plus B2 root 2, two elements from this set, and you multiply, you see that A1, A2 plus 2 B1, B2 plus B1, A2 plus A1, B2 times root 2. For A1, A2, B1, B2 rational numbers, all these products are also rational numbers. Therefore, what you see over here is a rational number plus a rational number times root 2. An element in, this is an element in the set Q of root 2, right? Q of root 2. Therefore, this is closed under multiplication. And multiplication is associative. Once again, it's an inherent property from R, from the ring R. And not only that, distributive laws also hold, which you can check on your own, right? Those things you can work them out. I will simply write, this is associative and distributive laws hold. Therefore, by definition, Q root 2 is a ring, and furthermore, it's a subring because it's a subset of R. Because Q of root 2 is a subset of R under the usual addition and multiplication. Under usual addition and multiplication. So we see that this is a ring under usual addition and multiplication. Now observe, now we want to see what are the units of this ring, or whether we have units, right? Okay. Obviously, this has the unity. Now, unity is different from a unit. Unity will always be a unit, but not all units are or is unity, right? Unity is simply one. One is the multiplicative identity one is what we call the unity, right? So first observe that this is a ring with one, the unity, one which is simply 1 plus 0 times root 2, an element of this set, this ring. Therefore, Q of root 2 is a ring with unity 1, which is actually different from 0, right? Now let's take some non-zero number. We want to see whether it possesses a multiplicative inverse, right? For every a plus b root 2, which is not equal to 0. So it's a non-zero element that you take from this ring. If this is non-zero, this means one of A or B must be non-zero. Both can't be 0 at the same time. One of A or B must be non-zero. So I'll write that is one of A or B must be non-zero. Not both can be 0 at the same time, right? For every non-zero element that you take, we have, when you take this multiplication, a plus b times root 2 times a minus b root 2, this product will give you, because we are doing the usual multiplication, a squared minus 2b squared. Now, this is non-zero. This multiplication is non-zero. This value over here is non-zero. Why is that? A and B are not zero at the same time. One of those must be non-zero because we are taking a non-zero element, right? This is non-zero because of that. Now, this implies a plus b root 2. If I multiply, because it's a non-zero number, you can multiply both sides by a squared minus 2b squared times a minus b root 2 over a squared minus 2b squared. This is equal to 1, right? This is equal to 1. Not only that, what you see over here is an element of Q of root 2. How can we see this? If we rearrange the terms properly, we have a plus b root 2 times, all right, a over a squared minus 2b squared minus b over a squared minus 2b squared times root 2. This is equal to 1. Now observe, this is an element in the set of rationals. A is a rational, a square minus 2b squared is a rational number, right? Sorry, a is an integer. When a and b, this is a rational number, this is a rational number, right? Therefore, what you see over here is this whole thing, this whole number is an element in Q of root 2, right? So now you take for any non-zero element a plus 2b squared that you take from this ring, you have another element in the same ring where when you take the product of the two, you end up with 1. What does it mean? By definition, this number is the multiplicative inverse of a plus b root 2, right? So we have a minus b root 2. I will simply write it in this form, a squared minus 2b squared, to be the, or is the multiplicative inverse of a plus b root 2. And this non-zero element is chosen arbitrarily. What does it tell us? All the non-zero elements in this ring has a multiplicative inverse, have multiplicative inverses. In other words, every non-zero element in the ring Q of root 2 is a unit. So by definition, and because the multiplication is commutative, it's a division ring that is commutative. By definition, Q of root 2 is a field, right? This tells you every non-zero element is a unit, so that Q of root 2 is a field. Q of root 2 is a field. Right. Next topic is integral domains. Okay, I'll start off with the definition. Now, this is something that we have actually considered when solving or when finding roots of polynomials, right? For example, what do I mean by this? If you consider, before we actually get into before we get to the actual definition, let's take, I will simply refer to the same example that you have in your textbook. Suppose you have this polynomial x squared minus 5x plus 6, and you're asked to find its roots. It has at most two distinct roots. At most two roots, right? How do we solve this? We equate it to 0. We factor it out. So we see that this is simply minus 2 and x minus 3, right? So we have, without even, now we have two elements, right? Say that this is, all the coefficients are coming from z, right? You have two terms, the product of two terms to equal 0. So what do we conclude at this point? We say that then one or the other must be 0, right? So the only possible values for x in this case, so that this entire polynomial ends up being 0, would either be when x is equal to 2 or when x is equal to 3. So we simply conclude and say that the only possible values are 2 and 3. Is it always the case? So far, with all the problems that we have done with respect to polynomials and finding roots, yes. Right? Yes, because we have the solutions always lie in most of the problems as real numbers or even complex numbers, both of which have no zero divisors. When we get to this part, you will understand, right? But it's not always the case. In order to understand that, we come to this definition. If we have a ring R and A and B are two non-zero elements of this ring R, right? If A, B are two non-zero elements of a ring R, such that their product gives you a zero. We have two non-zero elements, but the product itself gives you zero. Then we say that A and B are divisors of zero or zero divisors. Or zero divisors. Or we simply say zero divisors. Now, the set of integers. Now, if you compare it to this example, over here it says you are taking two non-zero elements. You are taking non-zero elements. You're taking non-zero elements. But the product ends up being zero. If that is the case, A and B are divisors of zero, or in other words, zero divisors. But when it comes to finding solutions or roots, so far what we've done, once you get to this point, with the factors equating zero. So you see a product giving you zero. Without any further discussion, we simply say one of this, right, must be zero. One of this must be zero. They both can't be non-zero at the same time. We simply deduce it. Right? Now, obviously, with the rings where the roots lie most of the time for these polynomial problems, they have no zero divisors in those rings, in those fields. Right? For example, Z has no zero divisors. Why is that? Take any two non-zero integers. You take any two non-zero integers. Once you take the product, you will never get it to be zero. You take any two non-zero integers, the product will never give you zero. The product will never give you zero. On the other hand, if you look at an example of this form, let's take Z6 with the elements 0, 1, 2, 3, 4, 5. Right. Now observe in this case, I will take the non-zero elements 2 and 3, right? When you multiply 2 and 3, how do we define multiplication over this ring? It's multiplication modulo 6. So you multiply, I will simply denote it by multiplication modulo 6. Divide, or you take the product of 2 and 3 in the usual sense, divide it by 6, take the remainder. So 2 times 3 is 6, divide by 6, the remainder is simply 0 because it is divisible by 6. Now you see, with two non-zero elements, the product gave you a 0. Right? Not only that, if you take 3 and 4, 3 times 4, when you find the product in this set, it gives you a 12, and 12 is divisible by 6. Therefore, there is no remainder. So now we see that 2, 3, 4, all three are zero divisors because those are non-zero elements where the product gives you a 0. By definition, those are zero divisors. So if we try to say solve this in a ring of this type. Now, obviously, because we have 6 over here, it's not, let's say you asked to find the polynomial or solve the polynomial in the ring of Z12 or something, then you can't simply conclude the one of this must be 0. You can't conclude one of this must be 0. So when it comes to other rings, you have to be a little bit careful, as you can see in this example. Now in this case, we can write 2, 3, 4 are all 0 divisors. Now observe 1, 5, the non-zero elements will never be 0 divisors. 2, 3, 4. But if you compare it with 6, what do we see once again? Those are the only elements that are not relatively prime to 6. These are the only elements that are not relatively prime to 6. Right? And we write it as a theorem next. But first, let me note down these are the only elements 6, Z6 that are not relatively prime to 6. Now we write it as a theorem for this specific ring Zn. In the ring Zn, the 0 divisors or divisors of 0 are precisely those non-zero elements that are not relatively prime to n. So all the non-zero elements that are not relatively prime to n, if there are any, will be 0 divisors in the ring Zn. How do we prove this? Okay. Let's take M to be an element, a non-zero element in the ring Zn. And let's suppose it's not relatively prime to n. So let's take M to be an element in Zn such that M is non-zero and it's relatively prime to n. That means their greatest common divisor is simply, not relatively prime to n, not relatively prime to n. Let's take it to be d, which is not equal to 1. If it is not relatively prime to n, the greatest common divisor must be greater than 1. Okay. Then, now d is a common divisor of m and n. Right? When you divide m by d, you get an integer. Divide n by d, you get an integer. So we see that we can write m times n over d, right? M is an integer, n over d is an integer because d is the greatest common divisor between m and n. D divides both m and n. You can sort of rearrange it and write m over d times n. So the product of these two integers is a multiple of n. You have m and the integer n over d, both of which are elements of Zn. Why is that? M is already taken from this ring. Now, d is the greatest common divisor between these two, which is greater than 1. So n over d is an integer that is less than n. That is less than n. So it belongs in this set. So you have two integers now, two elements that are in this set, where its product, the usual product that we see over the set of integers, gives you this, a multiple of n. So when you take the product of these two, now this, I will simply write a multiple of n. And observe that n over d is an element in Zn. So when you take the product of m and n over d or in Zn, that means you take multiplication modulo n. So we have m over d. The product over here, if we refer to multiplication modulo n times n, is simply 0 in Zn. So the multiplication of these two numbers, that is m cross n over d, is simply 0 in Zn. You have m to be non-zero, n over d is non-zero, right? N over d is also non-zero because n is non-zero, d is non-zero. Their division in the usual, it's a non-zero integer that you get, which is less than n, a positive integer, non-negative integer, which is less than n, right? Now you have two elements that are non-zero in Zn, but the product itself produces or gives you a 0. What does it tell you? M is a zero divisor. M is a zero divisor by definition. M is a zero divisor. On the other hand, if you have an element in this set, Zn, which is relatively prime to it, right? On the other hand, let me write, on the other hand, if M in Zn is such that the greatest common divisor between M and N is equal to 1, right? That means they are relatively prime. For uh, mm, for S in Zn, if we have M multiplication modulo n times s to equal 0. Now you're taking M, an element in this set, which is relatively prime to n, and if for any other element in the group, you have the product to be 0, right? 0, then we must have n to divide the product ms. Now, what does this give you? M multiplication modulo n times s equaling 0. That means you multiply m and s in the usual sense. You take the product ms, divide by n, you simply write the remainder. But the remainder gives you a 0. That means the product ms is divisible by n. Right? The product ms is divisible by n. So that means if m is relatively prime to n, n must divide s. N must divide s. Okay, so let me write, then we must have n to divide ms, the product of m and s as elements in the ring Z, since we know that the greatest common divisor between m and n is 1. In other words, those two are relatively prime. we must have, if n divides the product ms and n and m are relatively prime, we must have n to actually divide s. If s is divisible by n and s is taken from this ring, we must have s to be 0 in Zn if it is divisible by n. So that concludes the proof.